Hello. So this is my website. If you want to go through that, and this is my WhatsApp number, so you can contact that one. So today we are going to be discuss about electric field at the center of the uniform charged semicircular ring. So that has the radius is the R, capital R, and the total charge we are going to define is the Q. So our target is to find out the electric field due to this semicircular arc at this point, at this center of the point. So that is, so let's for that, we are going to be assume the dq element, the small element, because this is the continuous charge distribution that we have it. So for that, we are going to take it a dq element that is on the ring. So due to this dq element, the electric field at this point, so at this center, so I'm going to write this is the electric field direction because it is always goes away from the positive charge. So at this point, I have to show the electric field at this point is will be like this. So this is the name I'm going to give the DE vector, a small electric field due to the DQ charge over there. So now, so let me take it the x coordinate systems that we have it. So this is, let me make it the x coordinate. This is, let me make it the y coordinate. And because we are going to split that few the things. So x component. So, and this is the d theta. I'm going to take it the small angle. This is the d theta. I'm going to take it. And this is the dq charge and the charge length where it is spread it out. Let me take it the width of that one is this width. The arc length, I'm going to take it dx. And the charge distribution is over there. The dq is the charge distribution over a small arc, that is the dx, and this is the d theta. So I'm going to take it, this is the theta angle. So with the y-axis, I'm going to take it, this is the theta angle. So this is vertically opposite. If this is theta, this is also have to be theta. So let me take it the angle, what will be the component of the DE vector in the x direction and the y direction. So let me assume it, this is the x direction, this is the y direction that we are going to take it. So if I'm going to split that component, if I'm going to split that component, it come out to be in this direction, in the x direction is going to be come out DE sine theta component. And in this direction is going to be come out to be cos theta component. Do not get confused with the horizontal and vertical basically. This because this is the theta that is given. So the adjacent to the theta, that is dE cos theta always. So we split it apart. We split it basically dE cos theta in the x direction. So I'm going to write it. This is dE x component of that one. This is the y component of that. dE in the y component, the vertical component. So if I'm going to apply the similar ideas, so this is, let's suppose this is the same angle. I'm going to take it the dx element here also that had the dq charge. Due to this one, the electric field component will be like this at the same angle. I want to show you something. So this is dE element. I'm going to take the same distance, r radius is the same, dq will be the same charges over there. So DE, the same electric field will be there, but in the obviously in respective to that direction. So this is the angle theta. So again, I'm going to take it. This is component is going to become out to be cos theta in this direction. So in this direction, so let me write it with the white one. So this is DE cos theta, DE cos theta component, and in this direction is DE sine theta. If you look at this carefully, DE cos theta is opposite and they are equal. So they have to be cancelled out. In the same way, if you take it the another DQ element here, and again they will cancel out. Every time DE cos theta is going to be cancelled out. That should be reflected in our calculations also. After that, we are going to do that. So And this dE sine theta means the component that is coming every time in the x component is going to be add up every time. That is not going to be give the zero result to us. If you look at this carefully, there is only the electric field component, net electric field due to that circular arc is only in the x direction that is going to be come out. And to represent that, so I have this is the ring, and this is the dE element that I had taken it over there. And so this is dQ element. And due to this one, so there is a electric field in this direction that we represented. And if I take the another dQ element, similarly, this is dE dash. By the way, it is if it is symmetric, it also have to be the same. And if I'm going to split it about the component is, so if you look at this vertical component are canceling out each other, there is only a horizontal component is going to be left up on that. So that the use of the symmetry case, we are going to be solve this problem by using that one. And this is the n is the number of the element, by the way. This is if I try to show to you, this is the dq element, the segment. If you want to divide it, to explain that one in the same way, you can divide it due to this impact of that one. You are going to find out the electric field every time vertical component of that is going to be cancelled out. So this is the case that we have it. So let me go with some of the more further calculation for that one. So for this, when the charge is distribution continuously on the length, so we define the linear charge density. Charge density I have to define first. That is with the lambda we define it, and that is dq by dl. dl instead of this is the dx element that we have it right now. Or we can define like this also, total charge by total length. So length is, by the way, this is a semicircular. So if I want that, I can use this equation also. Total charge by total length. Total length is pi r, semi circumference of a circle. So this is dE. dE is the uh, electric field, the small electric field with the dq charge over there. So that is going to become out to be 1 by 4 pi epsilon naught. That you should be aware of that. This is dq due to a small charge. This is the electric field is going to become out to be. And similarly, we can find it out in the x direction and the y direction. So let me write it in the x direction is going to become out to be dq by r square. In the x direction, we have the sine theta. And in the y direction, the element of that one is that is going to become out to be like this. Cos theta component. And now we have the x component, y component of the velocities, basically electric field, sorry. So then you have to substitute the dq, the thing is. So then let me come to this equation again. So we define the lambda. By the way, define the lambda like this. We make it like this. So the lambda is equal to, we define the lambda is dq, charge over the charge per unit length. So, and dq is going to become out from there is lambda dx. And one more thing, because the thing is, as I'm going to integrate that, the theta is, I'm going to take it as a variable, that theta. So for this theta, because this is the arc and r is the capital R is the radius for that one. So this capital R is the radius for this one. So I need that I should come with the theta something. I had to change this dx in the term of theta. So for this one, you can apply the concept is, if you have any other circular arc, on that circular arc, you have the circular arc, and let's put this in the center. I think we are aware of that. If the theta is in the radian, this arc length, the length, arc length is that theta is in the radian is going to be defined like this, L by R. So arc length of this. Right now that arc length, I'm going to take it very small arc length that I taken. So let's suppose this is d theta or dx. This is dx. For that there is a small change of the theta that I taken it. So I'm going to write it d theta is equal to dx r. So the dx is going to be come out from there is r d. So let's substitute the values here. So dq become now by putting the dx value, that is r d theta. So let's plug in the values. So dq is equal to lambda r theta. So let's plug in the values in the both the equations. Lambda r d theta divided by r. R is, I'm taking the capital R, capital R. So here I have written small r. So let me change it. Sorry for that. So, and let me take it capital R. So this is sine, because R is the distance from where you want to find it at this point. So in the same way, we have the dEy component, the same. It's come out to be the same. And the same thing, that is cos theta. To find out the total electric field, so I'm going to integrate the total electric field in the net electric field in the x direction. Then I'm going to integrate. This one is dE max component of that one. So let me cancel out the one of the r. That's sine theta. Okay. Lambda by r. So sine theta d theta. And I'm taking this constant outside, 1 by 4 pi epsilon naught. We are taking it outside. The integration of the sine theta is going to become out to be cos theta. And what will be the limit? Let's figure out the limit. Because this is the theta that I taken it. This theta is from 0 to 180, because that is a semicircle. So that is pi. So means that the theta is going to be go from 0 to pi. This is 0 to pi. Correct? So that is the x component I'm solving right now. That is 1 by 4 pi epsilon naught upper limit minus, that is minus sign, sorry. That is integration is minus cos theta. That is minus and minus cos 0. And that you have to plug in over there. So that is 1 by 4 pi epsilon naught. Sine pi is minus 1, so it will become plus 1. Minus minus become plus. Cos 0 is 1. So it is double of that. So it is simply come out to be 1 by 4 pi epsilon naught 2 lambda by r. This is the x component. If I'm going to solve for the y component, let me copy that one. So that is the component. If I'm going to y component, the y component, I'm going to get the net electric field in the y. I have to integrate that one. That is again 0 to pi. Everything I'm going to take it outside common of that. Lambda by r, that is the integration of cos theta d theta, and that is 0 to pi. Again, integration is the same. But now the thing is, if you look at this carefully, lambda by r, that is the sine theta, 0 to pi. And if you plug in the value, that is the sine pi is 0, by the way, minus sine 0 is 0. That is come out to be 0. And this is, we predicted that the y component have to be cancelled out, correct? The y component have to be cancelled out. So this y, to explain it, so this is 3D animation, so you can understand the vertical component have to be cancelled out, only the horizontal component is going to be remain. And you can think like this: if the dx element is every time it is moving any point, they are same and they are cancelling out each other. So this is whole story is that you have to. And as you get the horizontal component, as you get the vertical component of the electric field, so the total electric field you will get E is the total electric field is simply that is the square root of x component of the electric field, y component of the electric field. But the y component of the electric field is cancelling out, so this is become 0 eventually. So this is 0. So it is just come out to be net electric field. So the net electric field is only in the x direction, that is the x component that we have it. And if I substitute the value, net electric field in the x direction is going to be come out to be like this: 1 by 4 pi epsilon naught, double of the 2r. Thank you. This is the net result that we have.